My name is Katie Taylor-Smith and I'm going to be taking you through a review session on EpiData Analysis. The main objectives of this session are to recap on the basic setup, the basic functions of EpiData Analysis, to go through how to perform summary statistics using the commands on the menu bar, to look at how to create new variables, to go through how to perform simple bivariate analyses, and finally to go through how to use the editor to write commands into a program that can then be saved as a permanent do file. So this is the screen you see when you open EpiData Analysis. Up here is what we call the process bar, which is used for selecting commands and functions. This here is the results window or viewer where the results of your analyses will be displayed. And down here you have what's called the command line for entering commands manually. Few useful functions. If you go to Windows in the menu and you click on Command Reference, this brings up a comprehensive overview of the different commands and functions that are available in EpiData Analysis. The commands function gives you a list of the different commands that can be utilized in EpiData Analysis. The next function in that Windows drop-down box, variables, can only be utilized once you have loaded in data into the program. Data are read into EpiData Analysis, and this can be done by clicking on the Read button in the process bar. A box like this will appear, and here you go to the folder where your data file is located and select the data file that you want to load into the program and click Open. The green writing on the screen here tells you the name of the data file that's been loaded into the software, and it tells you the number of fields, 11 in this case, 11 fields or 11 variables, and the total number of records, 4,164. And down here at the bottom, this tells us that at the moment there are 4,164 records loaded into the program, and that green button tells us that the software is ready to be used. If we go back to the Windows function on the menu bar, and this time we click Variables, this brings up a list of the different variables that exist in our data set. We can browse our data by clicking on Browse in the process bar. This window will appear, and here we have a list of the different data variables that exist in our data file. We can either select specific variables or we can click All, press Run, and we get an overview of our data. Just to give you an insight into these data are from an HIV program in Burkina Faso, where in addition to HIV-1, HIV-2 also exists. And these specific data are for patients who've been started on treatment on ART between 2003 and 2008. And just to go through the variables, we have clinic, so whether the patient attended Roomba Clinic or Tarwu Clinic, the patient ID number, a unique patient identifier, TODAT, the date of starting ART, patient age, patient gender, HIV type, HIV-1 or HIV-2, patient weight at ART start, patient CD4 count at ART start, ART outcome, alive on ART, died, lost to follow-up or transferred out, and date of ART outcome. If you remember back to your Quest, Rec and Check file, in your check file for categorical variables, you could apply the value label function, where you assigned data labels to your data values. For example, gender, you could say 1 is male, 2 is female. If you've utilized this function, and if your check file is in the same location as your rec file, then you can use this toggle key here to switch between the data values and your data labels for your categorical variables. A useful way to see an overview of your data variables is using the command var, V-A-R, and this shows you information about the different data variables in your data set. It's reminiscent of your data documentation sheet. So we have the name of the variable, the type, the length. For your categorical variables, the data value and the corresponding data label. After your data have been read, data processing and analysis can then be performed. Data analysis commands can either be run from the process bar or they can be run from the command line. So we'll go through some different forms of analyses now, the most simple being a univariate analysis, where we analyse one variable at a time. For categorical variables, we tend to use frequencies and proportions, and for continuous variables, we tend to use measures such as the mean, the median, range, standard deviation, interquartile range, and percentiles. So we'll start with categorical variables, looking at how we generate frequencies and proportions. Using the process bar, we click on Analysis, and we select Frequency. And in this example, I'm going to look at gender as my categorical variable. So I click Gender, and I'm going to select row percentages, and I also want to see a confidence interval, and I'm going to click Run. And this is the output I generate. So N is the number of males and females, or the frequency of males and females. Next to that, the percentage or proportion of males and females. And next to that, the 95% confidence interval for those proportions. And up at the top here, we have the command that could otherwise be manually entered and run from the command line. You'll notice that the decimal places here are rounded up to 1 decimal place. That is the default setting in EpiData Analysis. We can change that, however. If you want to change the number of digits after the decimal place for percentages, we use the commands /D for decimal and then the number indicating how many decimal places we want. Often in operational research, it's more than appropriate to round your decimal places up to whole numbers. In other words, present to 0 decimal places. So let's just see how we do that. So here is the command that I ran previously, but this time I have added /D0 for no decimal places. And when I run that command, this is the output that I generate. And you'll see now that my decimals, my percentages are rounded up to 0 decimal places. So we've looked at how to summarise categorical variables. For continuous variables such as age, weight, CD4 count, etc., we can use the describe command to calculate the mean, the median, range, and percentiles. We click on Analysis in the process bar, and this time we select the describe command. In the pop-up box that appears, I'm going to select age as my continuous variable. I click Run, and the following output is generated. You see here, I've got age values for all of my 4,164 records. The sum of those age values, which is not the most informative of measures, the mean age, a 95% confidence interval for that mean age, the minimum age, maximum age, median age, and here what's called the interquartile range, which is the range of values between the 25th percentile and the 75th percentile. The question we have to consider now is, should we present the mean or the median? Well, it all depends on whether your data are symmetrically or asymmetrically distributed. If your data are symmetrically distributed, then both the mean and the median can be used. If, however, your data are asymmetrically distributed, then the mean is no longer a reliable measure of average, and you should use the median. But how are you going to know whether your data are symmetrically or asymmetrically distributed? The best way is to generate a graphical visualization of your data. To do this, we go to Graph on the process bar. I'm going to select Histogram. I select the variable of interest, click Run, and here is a histogram of our age data. These data are relatively well distributed in terms of symmetry, so symmetrical distribution. So in this case, we can present either the mean or the median, although most people will present the mean in preference to the median if data are symmetrically distributed. We've seen which summary statistics can be produced using the describe command. Another useful and sometimes more informative command is the means command. And to access the means command, we click on Analysis in the process bar and we select Means. Here I'm going to select age as my continuous variable again. I click Run and here is the output. This time I have the mean age presented together with the standard deviation, which was not presented through the describe command. And down here, the median age with the interquartile range. Just a word of caution, if your variable has missing data which have been assigned a specific value, for example 99, these need to be excluded before you run the describe or the means command. Otherwise, these values will be included in the calculations of mean, median, etc. And we can exclude these data using the select not command. So let's look at the example of the variable Oweight, which is patient weight at treatment start. This particular variable has missing data, indicated by the value 999, and we need to exclude these before running the describe command. At the moment, we've got 4,164 records ready to be analysed. If we now run the select not command on Oweight equals 999, you'll see that my records have gone from 4,164 to 4,132. And this includes all those records where Oweight does not equal 999. And now if I run my describe command on Oweight, you can see I'm working with 4,132 records. So as we saw in the previous slide, select not Oweight equals 999 in brackets selects all records for which the Oweight value is not 999. Subsequent operations will only be conducted on this data subset going forwards, unless you undo the selection, which you can do using the command select, and this will reinstall your complete dataset. Coming now on to generating new variables. Let's imagine we want to categorize a continuous variable such as age. Age exists in our current dataset in its continuous form, so let's imagine we want to categorize it into different groups. The first step is to define a new variable. We're going to make this a numerical variable and we're going to give it a character length of 1. We use the command define and then the name, we give a name for our new variable. I'm going to call it age group. So define age group, the hash key indicates it's going to be a numerical variable and it's going to have a character length of 1. If we now browse our data, you can see that a new variable called age group has been created, but it is still empty for all records. The next step is to indicate the categories for age group. And we can do this using the following command shown in yellow. So I'm going to say if age is less than 35, then my new variable age group is going to take the value 1. If age is more than or equal to 35 and age is less than 55, then age group is going to take the value 2. And finally, if age is more or equal to 55, then age group is going to take the value 3. The final step is to provide labels for the age group values, and we do this using the label value command. So label value, the name of my new variable age group, space, /1 equals less than 35 years, space, /2 equals 35 to 54 years, space, 3 equals 55 plus years. And you'll note that my labels are encapsulated by comma marks. This is necessary if your label is more than one word. And if we now browse our data, here's our new variable age group with the different data labels for each of our records. I'm going to take you through one more example of generating a new variable, this time recategorizing a categorical variable. And in this example, we're going to look at the variable outcome. So imagine we want to regroup outcomes according to whether they are favourable, anybody alive on ART, or adverse, anybody who has died, lost to follow-up, or transferred out. So we're going to have two groups, alive on ART and everybody else. We're going to call this new outcome variable bioutcome. So we create this outcome using the command define. Defined by outcome, it's going to be a numerical variable with a character length of 1, so 1 hash key symbol. And we're going to say if outcome is 1, in other words, if the patient is alive on ART, then we're going to give our new variable by outcome the value 1. If outcome is more than 1, in other words, if the patient is alive on ART, died, lost to follow-up, or transferred out, then we're going to give our new variable by outcome the value 2. We're going to provide label values. So label value, the name of our outcome variable by outcome, space / 1 is favourable, space / 2 is adverse. And it's a good idea to check that you've done your categorization correctly. So if we tabulate our new variable by outcome and compare that with the tabulation of outcome, the number of patients with a favourable outcome should be identical to the number alive on ART, which it is in this case. Okay, so we've gone through a univariate analysis before where we analyse one variable at a time. In a bivariate analysis, we analyse two variables at the same time. And there are essentially three variable combinations that we can consider. We can consider the analysis of two categorical variables, a categorical with a continuous variable, and two continuous variables. In operational research, we seldom analyse two continuous variables. So with this in mind, and in the interest of time, we are just going to look at these two variable combinations. For the analysis of two categorical variables, we compare proportions between groups, and for the analysis of categorical and continuous variables, we compare means or medians between groups. So let's look at the analysis of two categorical variables first, and this we do using cross-tabulation of data. So in this example, we're going to see how favourable and adverse outcomes, which form our new variable by outcome, are distributed by HIV type. We click on Analysis and we select Tables. And in the window that appears, the first variable I click on is going to be my outcome variable. And it's going to form my column variable. The second variable I click on is going to be my exposure variable, and it's going to be my row variable. And the convention, although it's not set in stone, is to make your outcome variable your column variable and your exposure variable your row variable. And that is certainly how EpiData Analysis will treat your data. I'm going to select row percentages, click on Run, and this is the output that I generate. Up here is the command that could otherwise be manually entered and run from the command line. And here we can see the proportion of HIV-1 and HIV-2 patients who have an adverse outcome. And it appears here that HIV-1 have worse outcomes than HIV-2 patients. 23% for HIV-1 patients versus 14% rounded up for HIV-2 patients. When we analyse a categorical and a continuous variable, we go to Analysis on the process bar, and this time we select Means. And in this example, I'm going to look to see how age is distributed by HIV type. The first variable I select is my continuous variable, and the second variable I select is my categorical variable. Click Run, and here is the output that I generate. So the mean age for HIV-1 and HIV-2 patients, and down here the median age for HIV-1 and HIV-2 patients. So these results suggest that HIV-2 patients are older than HIV-1 patients. The next step in a bivariate analysis brings us to significance tests. With a bivariate analysis, we're looking to see whether there's an association or a relationship between the two variables that we're analysing. If we observe a difference between the groups that we're comparing, we need to determine whether that difference is likely to have occurred due to chance or whether it's likely to be a true difference. And this is where significance tests come in. For the analysis of two categorical variables, we use the chi-squared test most often as our significance test. We use the Fisher's exact test if our sample size is small. For the analysis of a categorical and a continuous variable, we use the t-test to compare means between groups, and we use the Wilcoxon rank sum test or the Kruskal Wallis test to compare medians between groups. So let's start with the first analysis of two categorical variables first. So the chi-squared test. So to do the chi-squared test, in the command line we add the command space /t to our previous tables command. And just to note, the t here does not mean t-test. It is telling EpiData Analysis purely to do a test. And EpiData Analysis is quite clever in this regard, in that it recognises that we are analysing two categorical variables, and it knows that the most appropriate test is a chi-squared test. So we run that command, and this is the result of the chi-squared test. We have a chi-squared test statistic, which is the 6.186 figure that you see. And what we are particularly interested in is the p-value here, 0.0129, which we can round up to 0.01. This is smaller than 0.05, and therefore we have evidence that yes, there is a true difference between HIV-1 and HIV-2 patients when we compare them in relation to adverse outcomes, these two proportions, and also favourable outcomes, these two proportions. In the previous example, both our categorical variables were binary variables, meaning that they were only formed of two groups. But what if one of our categorical variables has more than two groups? As in this example. Here we are analysing the variable outcome with HIV type, and the variable outcome is a categorical variable with four groups: alive on ART, died, lost to follow-up, and transferred out. Again, because we are analysing two categorical variables, we do a chi-square test using our command /t, and here is the result of that chi-square test. The p-value, 0.0389, we can round up to 0.04, and this is telling us that yes, there is an association between HIV type and ART outcome. The result generated from that previous chi-square test would enable us to construct a table like such, where we are comparing HIV-1 and HIV-2 patients in regard to ART outcomes. And this single p-value gives us an overall impression of the relationship between HIV type and ART outcome. However, it does not allow us to do a deeper analysis in terms of where the actual differences lie between HIV-1 and HIV-2 in relation to each specific outcome group. So what if we want to compare HIV-1 and HIV-2 patients with regard to each individual outcome? What if we want to generate a table like such, where we are comparing each set of proportions using a p-value? To compare HIV-1 and HIV-2 patients in relation to each outcome, the variable outcome has to be recategorized into a binary variable for each outcome group of interest. So let's consider alive on ART first. So we're going to create a new variable. I'm going to call this new variable alive. So define alive, and it's going to be a numerical variable with a character length of 1, so 1 hash key symbol. And we're going to say if outcome equals 1, in other words, if the patient is alive on ART, then we're going to assign our new variable alive the value 1. If outcome is more than 1, in other words, a patient is reported as died, lost to follow-up, or transferred out, then we're going to assign our new variable alive the value 2. Going to provide label value, so label value alive /1 equals alive on ART space /2 equals other, anybody else. And now if I tabulate my new variable alive with HIV type as such, and I do a chi-square test using the command /t, here is the resultant p-value, 0.01 rounded up. And this is the p-value that you saw in the previous table. So here we are now comparing this proportion with this proportion. We have a small p-value, so we have evidence that yes, there is a difference between HIV-1 and HIV-2 patients with regard to the proportion alive on ART. A higher proportion of HIV-2 patients are alive on ART compared to HIV-1 patients. Let's consider the same for died. So we create a new variable, we're going to call it died, define died. It's going to be a numerical variable with a character length of 1, so 1 hash key symbol. And we're going to say if outcome is 2, if the patient has died, then our new variable died is going to equal 1. If outcome is 1, i.e. the patient is alive on ART, or if outcome is more than 2, i.e. the patient is lost to follow-up or transferred out, then our new variable died is going to take the value 2. We provide a label value command here, label value died /1 equal died space /2 equals other. And now if I tabulate my new variable died with HIV type, add the command T for my chi-square test, here is the resultant p-value, 0.06 rounded up, and that is the p-value that you saw in the previous table. And we would do exactly the same for lost to follow-up and for transferred out. Now the chi-square test is the most common and usually the most appropriate test to use when we are analysing two categorical variables. But there is a time when it's not the most appropriate test to be using. And the time when it's not is when you have a small sample size. And when the sample size is too small to use a chi-square test, then the most appropriate test to use is the Fisher's exact test. Fortunately, EpiData Analysis will let you know when it's more appropriate to use the Fisher's exact test rather than the chi-square test. So to demonstrate this, I am going to temporarily exclude a large subset of data. I'm going to use the select not command, and I'm going to use this to temporarily exclude all those records where age is less than 55. And you'll see now the number of records I'm working with has gone from 4,164 to 118. So now if I do my tabulation command with bioutcome HIV type and I do T for a chi-square test, you see this statement under the table. Cells expected less than 5, 1. The way a chi-square test works, in brief, is to compare the results that we observe with the results that we would expect if there was no difference between the groups that we're comparing. In that expected table of results, if any of the cell counts are less than 5, then it is no longer appropriate to use the chi-square test, and the more appropriate test is the Fisher's exact test. So whenever you see this statement below your tabulated output, this is essentially telling you that you need to use the Fisher's exact test rather than the chi-square test. So how do we do the chi-square test? Well, instead of T, we use the command EX for Fisher's exact. If I run this command, here is the result of the Fisher's exact test. And unlike other significance tests, this test generates a p-value directly. So p equals 0.52 rounded up. So for the analysis of two categorical variables, we've seen how to use significance tests to determine whether there's an association between HIV type and adverse ART outcomes. To quantify the strength or magnitude of this association, we can calculate a risk ratio or an odds ratio. And just to note, when calculating risk ratios or odds ratios, the outcome variable needs to be a binary variable. So the risk ratio and odds ratio can be calculated by simply adding the command /RR for risk ratio or /O for odds ratio to our tables command, like such. And here we have that command run and the result of that command, a risk ratio of 0.59 or 0.6 rounded up. Now, before trying to interpret this risk ratio, it's important to look at the information under the table, and this tells us which group we are comparing to which group in relation to which outcome group. So here we're comparing HIV-2 patients to HIV-1 patients. In statistics, we always compare the exposed group to the unexposed group. So comparing HIV-2 to HIV-1 patients. So with that in mind, the way we interpret this risk ratio is that HIV-2 patients have 0.6 times the risk of an adverse outcome compared to HIV-1 patients, or 40% lower risk of an adverse outcome compared to HIV-1 patients. Now, it just so happens that our brains are much better at interpreting a risk ratio that is greater than 1 rather than a risk ratio less than 1. So we can reorganize our comparison of groups to make sure that we do generate a risk ratio greater than 1. To do this in this example, we need to be comparing HIV-1 to HIV-2 patients rather than HIV-2 to HIV-1 patients. There are two ways of making sure that EpiData Analysis takes HIV-1 to be the exposure group. We can either recategorize HIV type. EpiData Analysis by default will take the group with the highest data value to be the exposure group. HIV-2 takes the value 2, HIV-1 takes the value 1. So if we change that around, then HIV-1 will become our exposure group. But there's a more simple way. And the more simple way is using this short series of letters. The way EpiData Analysis works is it will take the group sitting up top here as the exposure group. So if we can find a way of flipping HIV-1 and HIV-2 around so that HIV-1 sits on top, then HIV-1 will become the exposure group. And one way we can do this is by reorganizing how these percentages are presented. At the moment, these percentages are presented in ascending order, going from lowest to highest. If we reorganize this table so that they are presented in descending order, going from highest to lowest, so 23 sits up here and 14 sits here, then we will end up switching HIV-1 and HIV-2 around. And this is where this series of letter commands comes in. S for sort, C for column percentages, which draws our attention to these percentages here, and D tells us that we actually want to reorganize these percentages in descending order. In other words, going from highest to lowest. So if we run that series of letter commands, now you see 23 is at top and 14 under here. And by doing that, we have switched HIV1 and HIV2 around. And now if you look at the information under the table, HIV1 is our exposure group. If we look at the risk ratio now, we see it's a risk ratio greater than 1, 1.7, and that tells us that HIV1 patients have 1.7 times the risk of an adverse outcome compared to HIV2 patients, or 70% higher risk of an adverse outcome compared to HIV2 patients. So we've been through the analysis of two categorical variables, we've looked at significance tests, and we've looked at measures of effect size. For the analysis of a categorical and a continuous variable, we can use the t-test to compare means between groups, and we can use the Wilcoxon rank sum test or the Kruskal Wallis test to compare medians between groups. So let's look at the t-test first of all. And in this example, we're going to see if there is a difference in mean age between HIV1 and HIV2 patients. So on our process bar, we click Analysis and we select Means. The first variable I select is going to be my continuous variable, and the second variable I select, HIV type, is going to be my categorical variable. I'm going to tick Test Means, click Run, and here is the output I generate. And up here is the command that I could otherwise manually enter and run from the command line. So this is the mean age for HIV1 and HIV2 patients, and the p-value that I've generated from my t-test is the p-value shown here. It's a very small p-value, which indicates that we have strong evidence that there is a difference between HIV1 and HIV2 patients in relation to age. The HIV2 patients are generally older than HIV1 patients. The Wilcoxon rank sum test and the Kruskal Wallis test are used to compare the medians between groups. The Wilcoxon rank sum test is used to compare the medians between two groups, and the Kruskal Wallis test is used to compare the medians between 3 or more groups. However, EpiData Analysis only offers the Kruskal Wallis test. This we can survive with, however, because the p-values derived from both tests are mathematically identical when applied to the same analysis. So let's look at how we do the Kruskal Wallis test in EpiData Analysis. And for this, we're going to use the example of CD4 count and HIV type. So is there a difference in median CD4 count between HIV1 and HIV2 patients? Just to note, you must remember to exclude any missing values before running the analysis. In other words, any missing CD4 counts. So for this, I'm going to run the select not, and missing values for CD4 count take the value 9999. So select not, and then in brackets, TOCD4 equals 9999. After that, I can run my analysis. I click on Analysis, and this time I click on K Wallis in the drop-down box. Here, I select my continuous variable first of all, and then I select my categorical variable, HIV type, and click Run. And here is the result of that output. At the top here, the command that can otherwise be run from your command line. And this here is the p-value that we are specifically interested in. P equals 0.55 rounded up. So a small, or rather a large p-value. In other words, we do not have evidence that there is a difference between HIV1 and HIV2 patients in relation to CD4 count. And this is a summary of different bivariate analyses depending on what combination of variables you are analysing. Finally, we're going to go through how to use the EpiData Editor. Remember, changes to your data, so generation of new variables, calculations, etc., will not be stored in the memory. To make a permanent record of everything that you've done, For the purpose of reproducibility, sharing of analysis, etc., a program can be written in the EpiData Editor. And this program can then be run on consecutive datasets and can be shared with others for troubleshooting, for example. Essentially, the program is written in the same way as the command line entries are given. And we can access the program editor either by pressing F5 or by clicking on Editor in the process bar. This editor screen then appears, and this can be typed into just as you would a word processor. So in most cases, the editor program would be initiated as follows. First of all, a description of the program, in other words, what the analysis that you are looking at is all about. Now, we don't want EpiData Analysis to regard this as a program command. It needs to be regarded as a comment, and for that reason, we make sure there is an asterisk that precedes it. CLS clears the EpiData Analysis screen. The command close closes all files which may still be open. We then want to set the location of our file that we wish to open, CD followed by the name of the file location, and then finally read and the name of our file name in inverted commas. And this will open the data file of interest. So that series of commands would look something like this in the editor screen. Hitting F9 or then clicking Run will run the program through these steps. And here we've gone a little bit further and we've included here different commands that can then be entered as they would be typed at the command line. So here we've included the commands that we've used to generate our new variable categorizing age and the commands that we've used to regroup outcome into adverse and favourable. And now if we click Run or F9, this is the output we see in our results window. And that brings us to the end of this review session on EpiData Analysis.